I know that you all have a homework assignment due tonight, 11:59. I thought we could maybe see if anyone had any. Well, I've got one homework question already to kind of look at. But if there are other questions you have questions about, I'm happy to look at them, address them, do similar-ish problems. Oh, here's the attendance from everybody. Sorry if you got kicked out before. Those of you just getting here, there's the attendance form. You can scan it, do the usual thing. Let's see here. Lost something. Where'd you go? Okay, cool. I think we're all right. Chat again. All right. Let's see. I believe. Let me grab my notes here. Come here. Oh, also, I know what it was. For those of you in person, I do have some handouts for you that you can grab on the way out. You can pass around. Some of you might have gotten these already. It's the derivative worksheet. Didn't already get it. It's got derivatives on the front and it's on the back. So when you're working on, I'll put it over here kind of for me. Well, you can grab it on the way out if you want. And then here's another practice thing that I wrote solutions to, both on Canvas. So if you want more practice, you want. So these ones like answers, like pretty much show the word. But these ones have nice long solutions. So if you're looking for like more explanation, you want some practice problems, so just things that. And I guess I'll try and post the handout on Canvas as well. But I was having trouble doing that earlier. So yeah. But I'll do that for those of you if you want more practice. It's always good to have more practice. Pens. Come on in. This is the co-class for 16B, yes. All right. So let's see here. I believe. Let me see. Let me look around for a second here. I'm pretty sure we were looking at problem 3 from section 4.3. Yeah. Okay. So really, there's some fun numbers here. All right. I'm going to make up. Yeah, sure. Why not? I'll make up a slightly different problem. Let's say we have the following hideous thing. So we want to find the equation. This is an equation, but there's only really one equation of a tangent line. You can only really write it one way if you've got y equal to some stuff. It says find the equation of the line. Well, I'm going vertical. James, that's terrible. I usually go horizontal. Sorry, let me change it up. Okay, vertical is not going to work for me. Let's try this again. Sorry, one more time. So we want to find the equation of the line tangent to the following thing. Let's see, we've got y equal to, I'm going to make it, yeah, it's going to be real fun. X to the 7th times e to the negative x at the point. What have I got here? Sure. 7, comma 7 to the 7th over e to the 7th. Which, okay, I suppose I could simplify the 7 to the 7th with a calculator, but it's not super important. They do a similar thing in the problem here. All right, so to find the equation of a tangent line, you need 2 pieces of information. So we need 2 things. We need a slope, and we need a point. And we already have one of them. They were really nice. They didn't even just give us X, they gave us the X and Y coordinate, right? So sometimes, like if I was giving this problem as a problem, I probably would have written it as find the equation of line tangent to y equals x to 7 times e to the negative x at, I would have probably said instead of this, I would have been at x equals 7. And then you would have also had the job of finding the y coordinate of that point. But they were really nice in the summer problem. Like, we're just gonna give it to you because it's kind of a gross y coordinate, I'm not gonna lie. So to find, well, we have the point. It's 7, comma, whatever that terrible number is. Oops, not 7, not e to the 7th over 7 to the 7th, 7 to the 7th over e to the 7th. And then we need the slope. And of course, in calculus class, usually you're finding the slope by finding the derivative, right? Slope of the tangent line is one way of thinking of the derivative. So we have to find the derivative of this function. All right, that doesn't seem too bad. So we've got y equals x to the 7th times e to the negative x, I'm going to use the product rule. If you prefer, although I don't think you do, but if you did prefer, you could also use the quotient rule. You could write this as x to the 7th over e to the x and use the quotient rule. That would be an option as well. So let's take the derivative. So it's the derivative of the first piece times the second piece plus the first piece times the derivative of the second piece, and the derivative of e to the negative x is e to the negative x times -1. Cool. And now you might simplify. I might simplify. I don't know. Maybe. Oh, these problems are always. Oh, these ones are super annoying. I forgot what this one does. This is going to be kind of boring. Well, not boring. Kind of frustratingly lame in some ways. I think everyone's problem is like this. So if I write this out, let me simplify this because I think it makes it easier to see what's happening here. I have, in fact, I can factor out a lot. I can factor out an x to the 6th. I'm left with an x there, nothing there. And I can factor out an e to the negative x. So I've got factoring out x to the 6th, e to the negative x. I don't know why I put that in parentheses. There was no good reason to do that. And then from this first term, what am I left with after I factor out x to the 6th and e to the negative x? 7. From this second term, what am I left with after I factor out x to the 6th and e to the negative x? Yeah, negative x. Okay, here's what I consider to be a disappointment. When I plug in my x value to find the slope at that point, I'm going to get dy dx evaluated at x equal to 7 is going to be 7 to the 6th times e to the negative 7th times 7 minus 7. Oh. Which is nice as far as having to write the answer, because it makes it really easy to write the equation of the tangent line. If the slope is 0, well, here's my equation of my tangent line. Y equals mx plus b. So y equals 0x plus b. So y equals b. I said figure out what the b value is. Well, the line has to go through that point. So the b value has to be that y value there. I'm going to get y equal to 7 to the 7th over e to the 7th as the equation of my horizontal tangent line. And this is a horizontal tangent line because its slope is 0. So kind of a disappointing end to the problem, but that's what we get. I will mention, this is not the way I usually find the equation of the tangent line, in that if I were doing this, what I would actually probably really do instead of doing the slope intercept form is I usually prefer the point slope form, meaning I would have probably actually done it like this. I would have said, hey, instead of doing y equals mx plus b, let's do y minus y1 equals m times x minus x1. And then I would have gotten y minus the y coordinate, which is 7 to the 7th over e to the 7th, equal to 0 times, it really doesn't matter, but we'll write x minus 7. And that's going to yield the same result. This is going to give me y minus 7 to the 7th over e to the 7th equals 0, which gives me y equal to 7 to the 7th over e to the 7th. And that is how you should write it in grade scope, or whatever you could multiply out 7 to the 7th if you want to. You should not plug in e to your calculator and get a decimal approximation, right? Specific. I should be very clear about this. When you I mean, well, I don't know, maybe not. So when you are entering things in web work, unless they say they want a decimal approximation, you should be using the number e, like just e to the 7th. You don't want, right? I mean, I don't have the sure. You don't want to write 7 to the 7th divided by whatever e to the 7th ends up being as an approximation, which is, I don't know what. Let's find out here. E to the 7th is, let's see, e to the, oh God, I hate this dumb calculator. 1096.63, right? I do not want to write y equal to 7 to the 7th over 1096.63. That's going to come out to be probably wrong, because it's a decimal approximation, not the exact value. So Only give approximations if asked for. Otherwise, you should always be writing e or pi or whatever, not the decimal approximation, or square root of 2, right? We don't want 1.4. Okay. So questions about this one? Yeah. Sure. So like right here, I took the derivative. Super cool. And then so we actually probably didn't need to do the second step, but sometimes it is nice to factor out. So I'll actually go back and visit this again real quickly. But what I did was I factored out the greatest common factor. So I saw that both this piece, come on, pen, this piece here and this piece here, both had an x to the 6th. That's the highest power of x they both had. And they both had an e to the negative x. So I was able to factor both of those pieces out. From this piece, I'm left with just 7. And from this piece, I'm left with a -1 times an x. And so if I distributed this back through, I would get 7 times x to the 6 times e to the negative x, like I have here. And I would get negative x times x to the 6, so negative x to the 7th times e to the negative x, which is exactly what I have here. I will point out, though, that you didn't actually have to do this to get the right answer. It just makes it a little easier to see. If instead we had gone straight from the derivative equaling 7x to the 6th times e to the negative x plus x to the 7th times e to the negative x times -1. If we plug in 7 here, it's not impossible, but it is more challenging to see that we get 0. Here I'm getting 7 times 7 to the 6th times e to the negative 7th plus 7 to the 7th times e to the negative 7th times -1. We have to be a little bit more observant to be like, oh, wait, this is really just 7 to the 7th times e to the negative 7th minus the same thing, which ends up being 0. So I found it easier to see what was going to happen by factoring, and that is often true, but it is not always necessary. Other questions about this particular problem? Now, this isn't exactly like what was on your homework problem, but I imagine almost all of you, I think all of that problem, all the time, the slope of the tangent line is going to be 0, no matter what numbers you have. I think that's how this one works out. I'm fairly confident. So I think, yeah, like looking at this one here, yeah, totally the same idea.
The y coordinate, the answer is the 27 over e cubed.
Right, the answer is y equals 27 over e cubed, or 64, right, or whatever your power, right, whatever, right, that's 3 to the 3rd over e to the 3rd, or yours might be 4 to the 4th over e to the 4th, or 5 to the 5th over e to the 5th. It's going to be something like that, because that's the way this problem happens to work out. It's kind of cool. Other homework questions that I can riff on? Yeah. Sure. You want me to look at the one specifically in the assignment? Because I can definitely look at that one. Sure. I know there's one in here. Oh yeah, I've seen, yeah, this one. Okay, yeah. I'm gonna make it more fun. Let's yeah, sure. So I'm imagining we are looking at maybe question 6 from section 4.3. That's the one that's the only implicit problem I'm seeing in this here. So let's make it a little more exciting. Let's say that, oh yeah. Okay, we'll do this. Let's say we have e to the x squared y cubed plus x to the 5th minus y to the 3rd equals, I can't really change that. I guess I'm stuck with you. Am I stuck with you? It can be more exciting. No, I guess I'm stuck with you. Fine. Oh yeah, I know. Okay, fine. I'll make this a +1 up here. Sorry, I'm changing the problem a little bit. +1 equals e squared. Yeah, that's way more fun. It's still similar to the question. So I have e to the power of x squared times y cubed plus 1 plus x to the 5th minus y cubed. Oh, y cubed again, James. How boring. Equals e squared. We could change that. No, we'll find. Okay. And we want to find, let's see. We want to use implicit differentiation to find just the slope, right? Not the equation of the tangent line, just the slope of the tangent line at the point 1, 1. Not that it is super important, but I will point out 1, 1 is a solution to this equation. You don't need to see that or know that, but if you plug in 1 for x and 1 for y, this left side does equal the right side. Right here, I get e to the 1 times 1 plus 1, which is e squared, plus 1 minus 1 equals e squared. Oh yeah, that checks out. Okay. So implicit differentiation, we always have to remember, and I feel like I see a couple new faces, so I'm going to say this a couple extra times here, that y is our quote unquote stuff, or our function of x. So that when we differentiate some stuff to a power, we get that power times our stuff to the less power. Then we use the chain rule and we multiply by. Thank you. Yes, the derivative of the stuff. We're always multiplying by the derivative of the stuff when we're using the chain rule, which we are always using when we were doing implicit differentiation. In fact, when you hear the words implicit differentiation, you should be thinking, oh, I'm using the chain rule all the time. Those like go together. So I'm going to write this again. I got e to the x squared y cubed plus 1 plus x to the 5th minus y cubed equal to e squared. Okay, so everyone's favorite derivative, the easiest derivative. What is the derivative of e to the x? Yes, it's the best. Okay. So that means the derivative of e to the stuff is e to the stuff times the derivative of the stuff. So here's my stuff. The derivative, differentiating both sides, I'm going to get e to that same stuff times the derivative of that stuff. And depending on how much work I feel like doing at the moment, I might just write the derivative of that stuff like this in kind of a lazy way. I could actually just do the work, but I'm going to do it in 2 steps. Okay. X to the 5th is straightforward. It's not a complicated thing. It's just a power of x. Its derivative is 5x to the 4th. The derivative of, so x to the 4th, the derivative of x is just 1. Y to the 3rd, the derivative of y isn't just 1. The derivative of y is the derivative of y. That's y prime or dy dx, whatever you want to write. So when I take the derivative of some stuff cubed, I get 3 times my stuff squared times the derivative of my stuff. And you can write y prime, you can write dy dx, whichever you prefer. I like to write y prime.
Multiplied it times the stuff because.
Times not the stuff, times the derivative of the stuff. Because of the chain rule. Because if we were taking instead, say like the derivative of x to the 4th plus sine of x quantity cubed, the derivative of some stuff cubed is 3 times that stuff to the 2nd power times what? Which in this case happens to be 4x cubed plus cosine of x. But in this example, what I'm saying here is y is playing the role of x to the 4th plus sine of x. So that's my stuff. And then the derivative of some stuff cubed is 3 times my stuff squared times the derivative of my stuff. That's exactly what's happening right here. The derivative of some stuff cubed is 3 times my stuff squared times the derivative of my stuff. So you can see the bottom part there. Does that help clarify things a little bit? Okay. The idea behind implicit differentiation, just to kind of back up one step, is that it is implied but not explicit that y depends on x. Essentially, we are making the assumption, although it's not really true, but we're going to go with it anyway. We're assuming that y is a function of x. So really, right, maybe y is equal to x to the 4th plus sine x. I don't actually know what y is because I can't take this equation and actually solve for y. But if I could solve for y would be some function of x. And so when I differentiate some function of x cubed, the derivative is 3 times that function of x squared times the derivative of that function, or 3 times my function squared times the derivative of that function.
And we do it to the y, but not y to the x. Because
Well, so we haven't done it over here yet. We're gonna in a second. So yeah, you're asking about this though. Yeah. So the reason is we're assuming that y is a function of x, but we're assuming also that x is the independent variable. X is just x. It doesn't depend on anything else. It's doing whatever it wants. And so I could say, and I will say actually, the derivative of x to the 5th is 5 times x to the 4th times the derivative of x. Just one. So x is the thing whose derivative is just 1, where y is the thing whose derivative is the derivative of y, which is y prime. Okay, here's the part that often throws a lot of people. What's the derivative of e squared? 0. So the derivative of e to the x is e to the x, but the derivative of e squared is a constant. Plug it into your calculator, you get like 7.8, I think. Close enough. And the derivative of 7.8, last time I checked, right? If you graph e squared, it's a horizontal line at y equals approximately 7.8. And horizontal lines have what slope? 0. So the derivative is 0. So the derivative of this constant that doesn't have any variables in it must be 0. It's a common trick, right? People will often ask you about the derivative of e squared or pi squared or the square root of e, or things that don't have any variables in them but look kind of complicated, or sine of e, or right, something, right? The derivative of sine of e is not cosine of e. It's 0 because sine of e is just a number. I don't know what it is, but it's a number that is always the same value. It never changes. There's no variable. So if you look at something and you don't see, right, the trick here is also, right, e kind of looks like a variable because it's a letter, or it's really a number that's looking like a letter, right? It's a letter pretending to be a number, or vice versa, whatever you want to say, right? That's really a number, but we give it this name because we don't have a better way of writing it. And so it looks like you might get something else, but there's no x's, there's no y's, its derivative is 0. Okay, we need to do derivative one more time because I was lazy here. I didn't do that first. Let's go back here. So this is going to be e to the x squared y cubed plus 1 times, all right, to take the derivative of x squared times y cubed, I'm going to use the product rule. So I'm thinking of x squared is like my f, y squared, y cubed is like my g. So the derivative of x squared, so I'm going to get f prime times g plus f times g prime. So let's see here. The derivative of x squared is 2x. Leave the y cubed alone. Plus, now we flip it. We leave the x squared alone. And just like in the previous step, the derivative of y cubed, or the derivative of some stuff cubed, is 3 times my stuff squared times the derivative of my stuff. And then the rest, plus 5x to the 4th minus 3y squared y prime equal to 0. Now, this kind of problem, when I see implicit differentiation, there are kind of two ways things go. One way it goes sometimes is find the derivative, meaning take this thing and solve for y prime in terms of x and y. You get some terrible trash that has lots of x's and y's divided by other x's and y's. The other direction is find the slope of the tangent line at a certain point. So you could still do all that same trash work, do all the algebra, find y prime equals, I don't know, negative 5x to the 4th plus some other garbage divided by some terrible thing, and then plug in 1, 1. Or you could first plug in 1, 1, and then do all the algebra. It's going to be a lot nicer. So typically, if you're asked to find the slope of a tangent line at one specific point, it is usually in your best interest to plug in that point first. I should say not first, so plug in the point immediately after you take the derivative, and then do the algebra after that. Let's see what I mean. So I'm going to plug in right now. When I plug in, I'm going to get e to the, luckily they've also given us really nice numbers. X and y are both 1. So I'm going to get e to the 1 times 1 plus 1, which is e squared, times 2 times 1 times 1, plus 1 times 3 times 1 times y prime. Y prime is still y prime, right? It's not going away. So I get 1 times 3 times 1, which is 3 y prime, plus 5 times 1 to the 4th, which is just 5, minus 3 times 1 times y prime, which is 3 y prime, equals 0. So now I can solve for y prime without too much trouble, except the trouble is going to be I'm going to need another piece of paper, which is always terrible. Would really like to finish this problem on this page. Oh well. One thing I do need to do is I do need to distribute this e squared to each of those. So I have 2e squared plus 3e squared y prime plus 5 minus 3y prime equals 0. And then we need to collect all the y primes on one side, all the not y primes on the other side. I might as well bring, it doesn't really matter which side you choose. I'm going to bring the y primes to the right instead of the other things to the right. Either way is fine. So I'm going to get 2e squared plus 5 left on the left. Left on the left, yeah, left on the left. And positive 3y prime minus 3e squared y prime on the right. Then we factor out a y prime. Whoops, and we factor out a y prime, we have things that's multiplied by 3 minus 3e squared equal to 2e squared plus 5. And finally, we divide by this. So y prime is 2e squared plus 5 divided by 3 minus 3e squared. Or in other words, the slope of the tangent line, it is terrible. At 1, 1 is that 2e squared plus 5 over 3 minus 3e squared. I will point out, we could have done all the terrible algebra first. We could have taken this garbage equation and done the same sort of work, meaning distributed this e to the stuff times that plus times that, and then grouped the two y prime terms on one side, the other terms on the other side, factored out the y prime and divided by the terrible algebraic mess that's left over. But that's usually not the easier way to do it. So I would encourage you all, if you have to find the slope of the tangent line at a particular point and you're using implicit differentiation, as soon as you have differentiated both sides of your equation, that is the moment to then plug in your point, because it's going to make your life easier. Questions about this one? So I'm closing. Okay. All right. All right. Other questions from the homework, or other things from the homework that I can pretend like I'm doing a problem somewhat different. We can also move on.
Can you do an example of like number 5?
On which section? 4.3 or 4.3? Number 5. Ooh, yeah, okay. Ooh, I'm gonna expand on number 5. You get more, you get extra. So number 5 says the following. Find the second derivative of, let's make it a little different. So find f double prime of x for, let's say, f of x equal to 8 minus 3x times e to the 7x. And for extra credit, we'll do that first, and then we'll extra it up here. So first derivative. So let's see, what could we do here? You can kind of go two different ways here. You could just straight up use the product rule to start off with. You could also multiply it out first, and then I don't know. I don't think that's really any better though. I would probably just do it as is. So let's just apply the product rule. So again, thinking of, since I've already used f, let's call this u and this v, and my product rule is going to be a u prime times a v plus a u times a v prime. All right, so let's see. The derivative of u is a -3. Or I could say 0 minus 3, right? Because the derivative is 0. And then we're leaving this alone. Plus, switch it up. Leave the u alone. 8 minus 3x. And then the derivative of e to the stuff is e to the stuff times the derivative of the stuff, which is 7 in this case. Okay. So now here's what I would do. Usually it is in your interest to simplify things before moving on to taking the derivative. So if you've got, like, for example, in the last class, I think it was last class, we saw some logarithms that had really complicated insides, and we decided it was better to first use the rules of logarithms to write it out into simpler logarithms and then differentiate. That kind of idea applies all the time. If you see reasonable simplification to do before differentiating, it is usually in your best interest. I don't really want to do, I would really rather say factor out an e to the 7x from both of these. So I'm going to rewrite this as f prime of x equals e to the 7x times -3 plus 7 times 8 minus 3x. And it probably pays to simplify this as well. That's going to be e to the 7x times -3 plus 7 times 8 is 56. 7 times -3x is minus 21x. So I would probably rewrite this as e to the 7x times 56 minus 3 is 53 minus 21x. And that looks a lot like the first thing we did, meaning taking its derivative shouldn't be too terrible. It's very, very similar to the function we just took the derivative of. So now to find f double prime of x. So it's going to be the derivative of the first piece. So the derivative of e to the 7x is e to the 7x times 7 times the other piece left unadulterated, plus flip it around. Leave the first piece alone, multiply by the derivative of the second piece, which is 0 minus 21. Okay. And then if you're typing this into WebWork, you don't have to simplify it, right? You can totally write it like this, or you could simplify it. But simplifying it, what's the word I'm looking for here? Like if you just type this and you know this answer is right, then you're good to go. Whereas if you simplify it, you might make a mistake. It might come out wrong. You're like, So if you're ever unsure about something, like if you've simplified it because you wanted to, you can always go back to the unsimplified version and plug that into WebWork, and it should accept it. Yeah. Bonus. Yeah, bonus. What are the critical points of this function? Oh, critical points. So the critical points, I know it might have been a while since you took the previous quarter of calculus. The critical points are what you get when you find where the derivative has, or where the derivative is equal to 0. So the critical points we find by setting our derivative equal to 0, which is good that we already simplified our first derivative, right? If we look at our first derivative, we've got e to the 7x times 53 minus 21x equal to 0. That's much easier than having to first deal with this version of it right here. So if I set that equal to 0, I'm either going to get e to the 7x equal to 0, or 53 minus 21x equal to 0. So let's see. Let's do this one first. 53 equals 21x. X equals 53, which is a prime number divided by 21. So that's one critical value. And what about e to the 7x equals 0? What are my solutions there? Can e to a power equal 0? You say no or yeah? Okay, yeah. You can't, right? If you think about the graph of e to the x or e to the 7x or e to the, any kind of x, it's always above the x-axis. It has that horizontal tangent line at the x-axis. So this has no solution. E to the something is always positive. All right, we might as well continue with this one since we're already here. Is this a relative maximum? Minimum, or neither? This is a good refresher. So to see if a critical point is a maximum or a minimum or neither, I typically like to use the first derivative test, which is where you take your number line and you put in your critical values. In this case, we just have one. And then you ask yourself, on either side of that critical value, is the function increasing or is the function decreasing? Meaning, is the first derivative positive or is the first derivative negative? So if I pick a number larger than that, let's go big. Let's pick 1,000. I know 1,000 is bigger than 53 over 21. If I plug in 1,000 to this expression, what's e to the 7,000th power? That's not what what's that? Yeah, what I really meant to ask is e to the 7,000th power positive or negative? How about 53 minus 21 times 1,000? Negative, right? 21 times 1,000 is pretty big, and 53 minus it is going to be very negative. So when you pick a number larger than 53 over 21, you get a positive times a negative, which is going to be negative overall, which means that the function itself has a negative derivative, which means it is decreasing. On the other side of that number, I'm going to make a very easy choice. I'm going to pick 0. And generally, if you can pick 0, 0 is a good thing to pick. So 0 is definitely less than 53 over 21. If I plug in 0 for x, I don't actually care about the value. E to the 0 is positive. 1. 53 minus 0 is positive. And a positive times a positive is positive, which means the function is increasing since the derivative is positive. So the function was increasing, then it was decreasing, which means we had a maximum. So we have a maximum at x equal to 53 over 21. Again, I know that wasn't asked as part of this question, but it is something that we might revisit at some point in this class. We might not. We might be kind of done with it, but it's good to refresh your memory. Times, okay. Yeah, time. Anything else from this assignment that I should look at before we do other things? Yeah.
Okay, for this problem, we go back to the last page.
You can. Yes, I can. It's somewhere. This page here.
Yeah, on the second derivative, where did the 7 come from?
The 7 here. So when I was, if I call this A, oops, let's call this A and this B, I'm using the product rule. So this here is my A prime. That's my B. Here's my A. Here's my B prime. When I take the derivative of e to the 7x, so the derivative of e to the 7x is e to the 7x times the derivative of 7x, which is e to the 7x times 7. That's where that 7 is coming from. And I should say the general answer to that question is it's coming from the chain rule, because I had e to the stuff, and the derivative of e to the stuff is e to the stuff times the derivative of the stuff. Actually, I know what I want to do next. So I'm certainly happy to address another homework question if you all want. But before I do that, let me do a quick recap of the derivative rules that we've talked about regarding logs and exponentials. So, and I have like 4 versions of each rule, which I know sounds kind of annoying, but it's not. I mean, it is, but you know. Okay. Let's start with the exponential side. So exponentials, I would say that if you're, how do I want to write this? Yeah. If you're taking the derivative of e to the x, the derivative of e to the x is e to the x. And then there's also the chain rule version of this. It says instead of taking the derivative of e to the x, if you take the derivative of e to the stuff, you get e to the stuff times the derivative of the stuff. Some books write this in a slightly different way. Some people like to write this as the derivative with respect to x of e to the u is e to the u times du. It's the same meaning, it's just a different way of writing it. We're thinking here we're thinking here that u is our stuff, and so the derivative of e to the stuff is e to the stuff times the derivative of that stuff. It's a slightly different notation, but someone might say this, or you might see it in your book at some point, but that's another way of writing it. I don't usually like to write it that way. I like to write f of x, or really I like to write the word stuff, as you guys have seen. All right, so that's the nice version of the exponential derivative formula, where your base is wonderful e, but then your base might not be e. Your base might be a different number. So if your base is a different number, the derivative of, say, a to the x is a to the x times the natural log of a. I'll mention there's a requirement about a, but we'll talk about it in a minute. And then finally, the kind of full version is that the derivative of a to the stuff is a to the stuff times the derivative of the stuff times the natural log of a. So technically, this last rule is really encompasses all the rules that are above it. If you wanted to remember just one of them, you could remember that one. But you're never going to forget that the derivative of e to the x is e to the x, right? That's just kind of in there already. So these are what I kind of think about this one, and I'm like, oh, if it's just a to the x, I get a to the x times natural log of a. And if it's just e to the x, I get e to the x. If it's just e to the stuff, I get e to the stuff times the stuff. So they all are kind of enmeshed into this one larger rule. And I should point out that for our base, right, if you're taking the derivative of a to the something, your base needs to be positive and not equal to 1. Otherwise, we have domain problems. If you have a function that's like -4 to the power of x, it has some weird domain. Like, so on your own time, when you have a moment, I encourage you to go and look at Desmos and check out the graph of, so graph 2 to the x versus -2 to the x. Just to check it out. This one looks normal. This one, you can barely see it because it only has like points along the way, because -2 to the x power is only really nicely defined if x is a positive integer. Anything else, like, for example, just to pick an easy example, -2 to the 1/2 power is the square root of -2, which isn't a real number. And really any other fractional or decimal power is problematic. So this looks very dumb. We don't like, I mean, it's not dumb. It's just, it's not a nice continuous function that's defined everywhere, which is what we want. Whereas this is everything we want. It's continuous, it's differentiable, it's beautiful, it's got all the things. Yeah. So check it out sometime. It's neat. Let's look at the other side, the logarithms. So first and foremost, let me put some dots here. The derivative of the natural log of x, which is the log base e, but I'm not going to write that, is 1 over x. And then the chain rule version of that, the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. And yes, it is totally fine to write it as the derivative of the stuff divided by the stuff. I just don't write it that way because I like to emphasize the chain rule nature of the process. You do the derivative of your outer function, you leave the inside alone. That's why we're getting the 1 over the stuff, because the natural log of something is 1 over the something. And then after you've done the outer function and left the inside alone, then you multiply by the derivative of the stuff. So that's why I'm writing it like this, just to kind of really emphasize that nature. But then if you wanted to simplify it, you would totally write it like that. So, yeah. And then we have the other base version. So notably, I should point out these two rules here, those two rules there, are pretty much the same, right? The derivative of e to the x is e to the x. The derivative of a to the x is a to the x, and then you tack on the natural log of a. These two rules are pretty much the same. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. The derivative of a to the stuff is a to the stuff times the derivative of the stuff, and then you tack on the natural log of a. In fact, you could also tack on the natural log of e here, which is 1, and the natural log of e here, which is 1. We don't, because it would be silly, but they really are the same rule. In the same sort of way, the other base versions of the logarithmic derivatives, instead of tacking on a natural log of a that you multiply by, you tack on a natural log of a that you divide by. So the derivative of log base a of x isn't just 1 over x, it's 1 over x natural log of a. And the derivative of log base a of some stuff is 1 over your stuff times natural log of a times the derivative of your stuff. So when your logarithm has a different base, you end up dividing by the natural log of that base. When your exponential has a different base, you end up multiplying by the derivative of that base. Oh, is a just a variable like x, or is it a number like e? A is a number like e. So to kind of yeah, oh yeah, cool. All right. So for example, if I was going to take, sorry, I'm kind of getting off here. If I wanted to find the derivative of a to the x cubed plus tangent of x, so a. Let's try that again. I didn't mean to pick a. I meant to pick like a real number, not like a pretend real number. If I wanted to find, say, the derivative of 5 to the x cubed plus tangent of x. It would be 5 to the stuff times the derivative of the stuff, which is 3x squared plus tangent of x. Plus what? Thank you, secant squared of x. Committing crimes here. Times the natural log of 5. So a to the stuff times the derivative of the stuff times the natural log of a. In this case, a is 5. Or if I wanted to find the derivative of log base 2 of e to the 6x plus, I don't know, cotangent of 3x. Ooh, that's going to be fun. I'm going to get, so my outer function is log of some stuff. I don't care that's log base 2. I'm just seeing a logarithm. And I know whenever my function is a logarithm of some stuff, the derivative is 1 over that stuff. And then some more stuff. But first I'm starting off with 1 over the stuff. I guess I might also put in the denominator what? I also know I'm going to need to divide by eventually a natural log of 2. I usually like to put it at the end, but I didn't, so okay. And then I have to multiply by the derivative of that stuff. The derivative of e to the 6x is e to the 6x times 6. Chain rule again. Chain rule a second time. The derivative cotangent of 3x is the derivative cotangent of some new stuff. And the derivative cotangent of x is negative cosecant squared of x. The derivative cotangent of 3x is negative cosecant squared of 3x times the derivative of 3x, which is 3. So that's how we would tackle that sort of monstrosity there. Okay. I got time. So those are kind of rules you'll be expected to take with you going forward. So that kind of concludes the list of derivative rules. Like you've got product rule, quotient rule, power rule, chain rule, derivatives of the trig functions, and then derivatives of exponentials and logs. And that's kind of it. There's like, okay, there's not all, there's a few other trash things like the derivative of inverse trig functions and the other thing I'm about to show you, but that's kind of the whole list of all the things you might ever need to differentiate. I mean, they can get really complicated because you can take all these things and mix them together with multiplication, division, addition, subtraction, function composition to make it very challenging. But at the base level, you're kind of just applying all those rules in the correct succession to get where you want to be. All right, so, okay. The last kind of thing, and I definitely saw a problem like this on the next homework assignment. So the next kind of thing is, what if I want to find the derivative of x squared plus 2 to the sine x power? So this is different than anything we've seen because in previous problems, right, if you have x to a number, use the power rule. If you have a number to the x, use the exponential rule we just talked about. But if you have a variable in the base region and in the exponent region, neither of those rules is applicable. And this is where you are stuck having to use the process of logarithmic differentiation, which we did when we were first doing the derivative, right? Remember, I'll remind you all, when we first did like the derivative of 2 to the x, we took the natural log of both sides so that we could bring down that power. Bring down the power. And then we took the derivative of both sides. And the natural log of y was 1 over y times y prime. And the derivative of x times a constant was just 1 times the constant. And then we got y prime equal to y times natural log of 2. And then y prime was y times natural log of 2, which we know is the derivative of 2 to the x. So the derivative of 2 to the x is 2 to the x times natural log of 2. Or the derivative of a to the x is a to the x times natural log of 2. So we're going to use the same process for doing something like this, but the problem is it's more complicated now. So check this out. Whenever you see an expression like this where your base and your exponent both have variables in them, you need to, hopefully they'll have been not cruel and have given it to you as y equals something. If they just wrote it like this, it's kind of a jerk move, because they're kind of obfuscating the fact that you need to write it like this to be able to deal with it. I should say, technically, there's a formula you can memorize for something like this. I've never been able to memorize it. It's just like, it's stupid. There's some things you can memorize and you just shouldn't, because it's better to follow a process. It's generally my idea. So we're going to follow the same process. We're going to take the natural log of both sides. Why are we doing that? Exactly. If you have variables in your exponent, we do not want them there. And we take the natural log of both sides to allow us to use the rule to let you bring down the power. So sine of x times the natural log of x squared plus 2. Okay. So the main difference between this process and that process is when we take the derivative of both sides here, the right side is just x times a constant, and the derivative is 1 times a constant. On this problem here, when we take the derivative of the right-hand side, we're going to have to use the product rule, because you have sine of x times natural log of x squared plus 2. So differentiating both sides, you get 1 over y times y prime equal to product rule, derivative sign is cosine, times the other thing left alone, plus leave the sign alone, and the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. And then we are almost done. We just have to multiply both sides by y. I encourage you to do this as one step, but I'm going to do it as 2. So I'm going to multiply both sides by y to get y prime equal to y times all this jazz, cosine of x times the natural log of x squared plus 2. I am going to simplify this a little bit and write it as 2x times sine of x all over x squared plus 2, just so it takes a plus space. And then finally, the last step, which I feel like you could have done in that step as well, is to replace y with what it's equal to, so that we get y prime equal to x squared plus 2 to the sine of x power times all of that stuff. Cosine of x times the natural log of x squared plus 2 plus 2x times sine of x over x squared plus 2. It's kind of terrible. It's a little gnarly, but I will say, and we'll talk more about this on Friday. This process does always work in this way, where you write y equal to your function, you take the natural log of both sides, you bring down the power, you differentiate both sides, typically using the product rule on the right-hand side. You multiply both sides by y, and then you replace y with what it's equal to. And I will point out, like I promised you a few classes ago, whenever you have a derivative that looks like an exponential typing, even though this really isn't an exponential function, it's still like it's got a power that's a variable. That same function shows up in your answer, right? It's right there. So it always happens like that. It's kind of cool. Yeah, we'll do more of these on Friday. I think there's something else I wanted to say. I guess not. Oh, I know. As a reminder that on Monday we don't have class because I won't be here.